Let's look at ice cores and how they might record records of past environmental change from the water isotopes from the ice. And we can go back to this graphic to remind ourselves that initially the water isotopic composition will come from the ocean and it will have a value which is close to 0 per mil, and as water is transported from the ocean into the atmosphere and ultimately to the high latitudes, to the North Pole and the South Pole, the water vapor will get increasingly isotopically more negative. And the snow that will fall from this vapor over the North Pole or the South Pole will be isotopically relatively light, lighter than these values here. So now we can redraw that data on a graph showing the oxygen and the hydrogen isotopes. We can start in the top right-hand corner in the warm regions, where the isotopic composition is going to be closest to that of the ocean. The rainfall that's fallen in those regions has travelled the least distance from the source. So relatively, it will still have a composition that's closest to the source of 0 oxygen and 0 hydrogen. But as the vapor is transported from the equator towards the poles in this direction, the rainfall that falls from that vapor will get increasingly isotopically more negative. And when you get to the cold regions where it's forming as snow, we will have isotopic composition which is much more negative. And so now we have values here down to around about minus 160 to 180 in the hydrogen and about minus 25 in the oxygen. And you can see this data follows a straight line, and there's an equation on the graph. And this equation is called the global meteorite water line, and it's a property of the Earth's climate system. What we can use this for in ice cores is to say that if the snow has an isotopic composition that's around here, relatively isotopically positive, maybe the climate was slightly warmer than when the snow fell with an isotopic composition which is slightly more negative. Let's see how that works. Maybe this is your dream job. Here's someone from the Australian Antarctic Division, and they are taking out blocks of snow. You can see them piled up on the left-hand side and the right-hand side of this picture. And because we know that the snow is accumulating over time, and this is the top of the ice surface, we know exactly when this snow was deposited, and we know the temperature at the time it was deposited. So if you have a weather station and a person that's happy to go and dig pits in freezing conditions to collect the snow at different times of the year and for different years, for recent years, you can build up a calibration between the isotopic composition in those snow blocks and the known temperature and climate at that time, and then use that to go back in time to reconstruct past climates. And here's one example. So on the bottom left-hand side, we see a graph that shows the relationship, the correlation between the temperature, this is a monthly temperature, and the oxygen isotope composition of the ice. So that's the composition of the snow that fell at these different temperatures. And you can see there's a reasonably strong relationship between the isotopic composition of the ice and the temperature at the time that the snow fell. So now we can use the oxygen 18 in the ice to predict the temperature. And on the right hand side, now we have another example where in this time we have a yearly temperature. This is going back through time, and again we're plotting it against oxygen 18, and we have some error bars, some uncertainty for each one of these data points because obviously the temperature varies through the year. But again, you see the same relationship. We can go back and take ice samples, measure the oxygen 18 composition of the ice, and we can then predict what the temperature was at the time the ice was formed. Hopefully now you can look at one of these graphs from an ice core, and we can make some sense of it. So on the top, we have the oxygenating composition, which we now know that the least negative values are going to be warmer, and the more negative values are going to be colder. And this is depth. This is from an ice core, and you can see that they've gone down 2,000, almost up to 3,000 meters in depth as they've cored deeper and deeper. A huge effort. And they've then converted this same data set in blue in the bottom graph to time. And time is now in years, and it's in kiloyears or thousands of years before present. So where it says 20, this is 20,000 years. This is 40,000 years, all the way back to 100,000 years before present. So we're living here, and the isotope composition here is one of the more positive, or at least negative values. So it's a warm period, which is true. We're living in a warm period and interglacial. And then we have here a much colder period. This is the last ice age. And this line here is the warming from the last ice age. And then we have a period here from about 80,000 years all the way back through to about 20,000 years, where predominantly it was cold. We had an ice age, but we had these very rapid warming, cooling phases that occurred very regularly through that time period. And then the last time we had a climate equivalently warm to today is back in something called the last interglacial, and the ice core shows that, and that finished sometime around about 100,000 years ago as we get the first decline into colder glacial conditions. I'll take you and show you our isotope lab where we make these measurements. Here it is at UNSW, and it's called the Ice Lab. Here it is. So we do the ice core research. And because it has Antarctic ice in it, it's a biosecure lab. Only limited people can go in. You've got to have appropriate footwear and be lab safe, which I was. And here we go. So here's a quick view around the lab. I'll show you the isotope analyzer in a minute. First of all, there's the ice. It's locked away so that no one can access it. And you can see all sorts of different colour plugs on the wall. We've got emergency power supplies to make sure that if the power goes down, the ice never melts. Here's another container full of ice. We need special approvals to go in. More ice cores, more equipment. And then the isotope analyzer is going to come into view now. There's some water samples being analysed. That's the analyzer, a very boring looking black box. I'll show you that again later. And then the rest of the lab. It's all about biosecurity. So all the biosecure waste is its own bin. We have our own dedicated laboratory to go and prepare everything. And finally, some quite nice views from the top of the building out over the airport. So now you know something about how oxygen isotopes are preserved in ice cores. So when might it be an advantage to go and analyse an ice core and take the isotope measurements? What will it tell us? What are the advantages? And what might be the disadvantages of trying to get isotopes from ice cores? Have a think.